Okay, let's go ahead and look at chapter 15 of the Powell book. And this is our final chapter in the semester. So hold your applause and we'll get started. All right, by way of introduction here, for most of the semester we've been talking about optimization using deterministic models. Okay, we know what the parameters will be. And then we kind of switched gears when we went into Monte Carlo simulation, where we have the ability to simulate uncertainty in some of the parameters. Okay, so it would be nice if we could marry the power of optimization and simulation. Okay, because we know that even in optimization models, there likely to be some uncertainty in the parameters. Okay, but as I said, using solver pretty much assumes that the objective function is a deterministic outcome. Okay, but with Monte Carlo simulation, we can treat the objective function as our expected value. Okay, and then we can input or simulate uncertainty. Okay, so analytic solver platform is more powerful than regular solver and has the capability of doing optimization with uncertainty. Okay, but we have to look at some things. Okay, obviously it's not quite as straightforward and simplistic as using regular solver and deterministic models. So let's take a look at an example here from the text for Hastings Sportswear. All right, and this is a fairly straightforward model where the owner of Hastings Sportswear has to order a certain quantity of parkas. Okay, and he has to order them really about 6 months ahead of knowing what the demand will be. So there's a certain amount of risk involved. All right. But he was able to get a number of forecasts, his data guys. And so he was able to get a mean of what the forecasted demand would be. And the standard deviation and experience tells him that the standard deviation is typically twice what the number that they gave him. So there is a multiplier here built into the model. Okay. Now we initially, this is an optimization model, but we're not optimizing yet. So we initially set the order quantity, which is going to be our decision variable, to the mean. Okay. And so moving down, the demand is going to be the maximum of either 0 or the normal distribution, mean, and standard deviation. Now, the reason we use the max function here is because the standard deviation is quite large. All right. Or the doubled standard deviation is quite large. And so there is a possibility that we would get a negative number here. And so the max function is there to prevent getting a negative number. The regular sales will either be the minimum of the order quantity or the demand. Okay. You certainly can't sell more than you ordered, no matter what the demand is. All right. And you're certainly not going to sell more than what the demand is, despite what you ordered. Okay. The revenue is going to be, your sales times your price. Cost is going to be calculated from the data up here. Okay. Now we are concerned with leftover units. All right. If we order more than what demand will be, there will be leftover units, and we can sell them for salvage at 8% of the wholesale price. Okay. And so we are concerned with that value, and but primarily what with is the profit contribution. Okay, which is your revenue minus your costs. Okay, it's your regular revenue plus your salvage revenue minus the costs. And as the next slide is going to demonstrate, and as I demonstrated during our synchronous session last time, we are concerned with the mean of the contribution and of the leftover units. And when you, as we've mentioned, when you run a simulation, what happens in the output cell is the last value. It isn't the mean value. So we've used psi mean here in these two cells to record the mean of the simulation from these two cells. Okay? All right. So, as I mentioned, two outcomes are of interest: the profit contribution and the number of leftover units. So, what we have done, as I explained, is we have used the psi mean function to record the mean of those two values from the simulation. But when we do our optimization, it is the maximization of profit, or the mean contribution of our profit, that is going to be our primary objective. All right, and so we want to maximize the contribution subject to a secondary consideration for the mean number of leftover units. So we are concerned about leftover units also, because that represents money that we have spent that we can recover a little bit of, but we obviously want to minimize the number of units that we have. So when we run the simulation, again, remember we haven't really optimized anything yet. When we run the simulation, we see that we get a mean of profit contribution of about $12,000. But there is it can go as low as in the 70,000s, minus 70,000s. So there's a fair amount of risk here. It's a big standard deviation. You notice that the curve is almost invisible. It's so wide. This is a normal curve, but it's very, very wide. Okay, so there's a lot of variability in this simulation. Likewise, in the number of leftover units, the mean is about 154. Okay, and so that represents, again, a fair amount of risk. We want to minimize the number of leftover units secondary to maximizing our profit. So we found the mean of the profit contribution and the leftover units when we set our decision variable to the mean of the demand. Okay, but we don't know that that's optimal. All right. And so, how do we optimize this decision? Well, a very kind of simple way of doing this is by using a grid search. Okay. And another way of putting this is trial and error. What we do is we select a series of values that we want to test for the decision variable. In other words, we start plugging in alternative numbers there, and we rerun the simulation at each of these values, and we can see it going up and down, and if the model is simple, we can very quickly arrive at a conclusion. Okay, in this particular case, it is better to order too few, as we'll see later on. It is better to order too few than it is to order too many. Okay, it is better to not meet demand than it is to have a bunch of leftover units. Okay, and so that's what a grid search does. You just manually start plugging in numbers here, and see what happens. All right, but there is a better way, which we'll see on the next. So I'll show you how to do the sensitivity analysis when we do our synchronous session. I'll show you how to do it in Excel. But this is the result, and you can find this grid search or using sensitivity analysis, and that is the sensitivity of our mean profit contribution to order quantity peaks out at around 100 units. Okay, so it's about $15,000. So that is our optimal value, somewhere along there. And remember, this is based on some uncertainty, so this is not absolutely written in stone, but this is what we're looking at. Okay, in this slide, what we've done is added the minimum and the maximum values to the mean also in our simulation analysis. And as you can see, the maximum contribution increases pretty linearly with the order quantity, and the minimum contribution decreases linearly. All right. So what that means is that there comes basically the width between maximum to minimum uh, increases as we increase the order quantity, basically increasing the risk. All right, wider range of values. So you might intuitively guess that it's to our advantage to order fewer than 800 if we want to limit risk. Okay, and we said that the contribution the peak was at about 800. Okay, so if we actually wanted to limit our worst case scenario, we would order around 700 units. Okay, but this is this is open to interpretation, and we're not going to get into that there's a standard or a one approved interpretation. Okay, this is up to your decision makers. This is simply a tool to make an informed decision. Okay, if we want to vary two parameters at once and see the results, this should look fairly familiar. This is basically a two-way sensitivity table. All right, very much like the two-way tables in solver sensitivity that we used several chapters ago. Okay, but this is the sensitivity of the contribution to order quantity and price. And so obviously if the price goes down, then our contribution goes up. All right. But also, as you can see, as you if you go across, say you start at zero point 0.7 and go across, you can see that that the contribution peaks at about 800. All right, at 75 cents it also peaks at about 800. At 80 cents it peaks at about 700. Okay, that's how you read this table. So this is another handy tool for varying your parameters and seeing what happens. And that's what sensitivity analysis is all about, to see which variables have an impact on your bottom line. Now, since this is at the end of a semester where we basically used Solver to figure out almost everything, you're probably, why aren't we just using Solver to do optimization? And of course we can, but we wanted to show you that using with simpler models, it may not be necessary, okay? But obviously using a grid search, even using the simulation sensitivity built in to Analytic Solver platform is a kind of it's a more hit or miss or trial and error way of finding an optimum when we can just use Solver. Okay, so that's what we're going to talk about now. So let's talk about stochastic optimization. Stochastic simply means subject to uncertainty, and it is the to most of the models that we have been looking at this semester, which are deterministic. Okay, so when there is a problem that involves three or more decision variables, and a lot of our problems have had more than three decision variables, and also constraints, then doing a grid search either manually or automatically is not as useful. Okay, so we need to turn to more sophisticated methods. All right, and so we can use Solver as part of Analytics Solver platform. All right, we designate the output, as you might have guessed, and the output cell will contain a distribution. All right, so we have to tell Solver what part of the distribution we wish to maximize or minimize. Get that. So when we run the option using Solver, this is the result. The order quantity is about 780. You could round that up to 781. And our mean contribution is going to be about $15,000. Okay, so this is a little more straightforward and a little easier to do than doing a grid search. All right, and as I said, this is going to work better than doing a grid search when we have more decision variables, and it gives us a little greater precision. So using Solver is often the best way to go. So far, we haven't added any constraints to our model. And using simulation and optimization, we can add the normal types of constraints. But I want to talk about something called chance constraints. Okay, and earlier, a couple chapters ago, we introduced the idea of a tail probability. In other words, a probability that you will not make, for example, a positive profit. Okay, and so we can use chance constraints to put a restriction on tail probabilities. Okay, and we can do that by creating a new cell that represents, say, if we want to restrict the 10th percentile of the distribution, some of the tail probabilities, we can create a new cell, or we can in fact add that constraint right into the objective cell. All right, which is what I'll show you on the next slide. If the 10th percentile is negative, then more than 10% of the distribution falls below zero. In other words, the probability of a loss is greater than 10%. So we can restrict, we can set a constraint so that we choose a decision variable that puts the probability at less than 10%. Okay, and this is what's going to look like in the next slide. So in this slide, what I did, put the chance constraint right in the contribution cell. Okay, I didn't create a new cell for it. All right, and it turns out that when we impose that type of constraint, then as you might have guessed, whenever you add constraints, the objective value is less than, it's not as optimal as it was without that constraint. So our order quantity drops down to about 2, and our expected payoff is going to be about 14.7. All right, and as you can see on the right hand side, I've got a threshold set at 0, and we have 90% above 0. So our chance of a negative profit is less than 10%, which is what the constraint was designed to do. And finally, something that's listed in the text called two-stage problems with recourse. Okay, and so as you know, the way we've been treating the simulation is we have to make decisions before we know the uncertain outcomes. All right, why we do a simulation, to try and take our best guess at what the uncertainty will be. Okay, but and typically it's a matter of time. In the sportswear case, we had to make a decision to buy things before we knew what the demand would be. However, if it's possible to put off decisions for some decisions for a little while, then sometimes some uncertainties can be resolved. Okay, and if we can do that, then we're better off to make those decisions later on. All right. Choose to hold off on some decisions until we have more complete knowledge. Then we base all of our decisions on uncertainties, and the more uncertainties there are, then the more suspect our decisions will be. Sometimes we can't help it. Okay. But we might be able to take some problems and make them a two-stage problem. In other words, there might be some things that we have to decide before we know the outcome. All right. But in some cases, some of our decisions can wait until the uncertainty is resolved, and then we can make the rest of our decisions. And that's a two-stage problem. And in so doing, we eliminate some of the risks. So that's pretty straightforward. In some cases, we're forced to make a decision under uncertainty, but we don't necessarily have to make all of our decisions under uncertainty, and that is Okay, as I saw from this chapter and the last one, simulation is used to evaluate a model when some of the parameters are uncertain. But we also, in some cases, want to optimize our outcome. Okay, and so with one or two variables, we can use something like grid search. We can automate the grid search using simulation sense. But really, for three or more decision variables, grid search and even using automation is not going to be ideal. And so we can use Solver. And in fact, we can use Solver for, as we saw, for the simpler models as well. And we can add things like regular constraints. We can add chance constraints. Okay. And so we can marry the power of optimization, Monte Carlo simulation, to evaluate models that occur in the real world, where some things are deterministic and some things are subject to uncertainty. And that's it for this chapter. That's it for the text. So well done, everybody, and we'll see you later.